Hi everybody. Let me get this PowerPoint started here. Okay, so we missed another class session yesterday. We had actually in last week also. Sounds like there's more weather heading in for tonight. I wanted to go through my PowerPoint real quickly here. We obviously won't get to do all the things that I wanted to do for these past 2 weeks, but we'll make it work. So in general, our class is going to circle around area of polygons, and I'm going to abbreviate this a little bit for us. The first question that is often asked is, how do we find the area of a figure? And initial responses oftentimes have students that give us things like length times width. I want to point out that while many students and even adults jump to the formula in order to describe area, that is a method for finding area. It is not a description of the concept of area. Area might be thought of as the amount of space covered by the inside boundaries of a two-dimensional figure or figures. How do we find the area is another question. We may use something like length times width in order to find area, but that's fine if we have some sort of a rectangular figure or some sort of a figure that we can make into rectangles. Most figures we encounter in the real world are irregular figures. Some might even have curved sides, and we'll talk a little bit more about that next week when I see you guys face to face. But I wanted to take a look at a problem like this, where we might find a figure that has irregular shape. And we want to be able to use this moving and additivity principle in order to be able to find area. And so we might think of finding the area by taking a figure like this and breaking it up into a number of different rectangles. So in this case, this top figure here would then be a 12 by 30 rectangle. This figure down on the bottom would be a 10 by 25 rectangle. And this little figure in the middle might be a little bit difficult to figure out, but we can see that this whole side is 15 and this side is 10. That should give us a side here of 15 take away 10, or 5. This side right here, we can use the same idea to have 30 as this whole length here, and this is 18 here. So this side right here should be 30 take away 18, or 12. We would take the length times the width. For this it was 12 times 30. That would give us 360. This pen's not great for this, but we have 5 times 12, which is 60 here. And we have 10 times 25, which would give us 250. Oh, that's not working. There. Anyway, the sum of those three figures would give us something that was 670. And we don't, I guess we're in feet here, so we would say that this is in square feet, thinking back to our discussions about dimension from the last chapter. Now, another way to do this problem might be to think of taking this figure and breaking it up in a variety of different ways. This is another way that we might break up the figure. In this case, we would have a 12 by 18. We would have a 27 here, 15 and 12, by, this would be 25, take away the 13, so this right here would be a 12, so I'd have a 27 by 12 in the middle and a 13 by 10 on the end, also giving us a combined area of 670. And there are other ways that you could do that too. Those are just two examples. You could break this up into triangles and do all sorts of things. Those are the two common ways that you would do that. But we are using this idea of additivity here, and that we can break up a shape into smaller pieces and then recombine them in order to find an area. And this works with all sorts of shapes. You can see this is a figure from the Beckman book where we have some sort of a figure, and we take this top portion and essentially cut off that top portion and move it down in the bottom here in order to make this bottom figure here, which then, well, I guess it looks like they have it the other way around. They cut off the bottom section and put it onto the top section. But either way, we are using this idea of moving, in this case, to move pieces to fit other pieces of the figure. And so that's the idea of the moving principle. And we'll be using this a lot as we look at various areas as a strategy in order to figure out total area of figures. Likewise, this is another example from the Beckman book where we might use additivity or moving in order to be able to solve this problem. In this case, there are a number of different ways that we might approach this problem. One way that we could do this is we could think of this as an entire rectangular figure, something like this. Not the best representation, but work. And we could subtract out the area of these triangles in the corner. So we oftentimes want to think about the shapes that maybe we don't necessarily initially see. We want to think about larger shapes and try to see if there are things that you know in order to be able to use this idea of additivity in order to find a total area. So quickly, I know I asked you guys to do a geoboard assignment. That's in the Dropbox in the week 06 folder to the Dropbox. And what I want you to do in this geoboard lab is to find area by breaking up the shape into smaller portions that are easier to count. And those, you'll see that the geoboard, the National Library of Virtual Manipulatives that have a lot of great manipulatives that you can use online with students or even for yourself, will allow you to use virtual rubber bands in order to carve up various areas the same way that we were carving up those previous examples. Remember that we are not looking for you to be able to regurgitate formula here. We want to practice our skill of using the moving and additivity principles in order to be able to find those. On the geoboard, the small square on the geoboard is your unit of measurement. When we find things on geoboards, I usually leave them in units squared. The geoboard link is here. Also, if you just run a Google search for virtual geoboards, it'll take you, I think probably your first option will be to the National Library of Virtual Manipulatives, but you can also go to nlvm.usu.edu and play around in there as well, but it shouldn't be too difficult to find. If you're having trouble, you can cut and paste there. And I had intended for this to be a group exercise, but you're going to have to explore these on your own. Well, you don't have to explore it on your own. If you guys want to get together, that's fine also, but each person will have their own lab to turn in next time. Also in the Dropbox, I have some visual proofs of the formula for the area of a parallelogram, and I'd like you to go ahead and you can follow the instructions here. It's basically just cutting out and creating different shapes and showing that the various formulas that we know are derived from the idea of the moving and additivity principle. So you'll do that for parallelograms, you'll do that for triangles, and you'll do that for trapezoids. And again, I've provided you trapezoids and that you can and figures that you can cut out in the Dropbox in the week 6 folder. One thing that we want to keep in mind when we're talking about triangles and bases and heights is that it's not always obvious what is the base and what is the height of a triangle. In fact, anything could be the base of a triangle. We want to use bases advantageously to think about how we might do that. And so here are 2 examples. You may not think of this triangle over here as having a base of AC, but if we think of it as AC and we know that this line H is perpendicular to AC, we know that the height then would be D to B. Likewise over here, it's difficult. We might think of this same figure as having a base of AB and a height of H over here, of CE over here. In this case, we're extending the base so that we can create a perpendicular and find the height. So there might be more than one way to find the height in order to be able to solve some of these problems, and they can get rather in this case, I'll run through some of these of what we might think of as bases and heights of these figures. So in the case of figure A here, B is the base. They have that denoted here. If B is the base, then this would be the height of the figure. In this case, if B is the base denoted up here, then this would be the height of our figure. This one's a little bit easier to see. If I have a base of B, I would have a height something like this. And here, if I have a base of B, my height is going to be something like that. And that's useful because that principle of shearing that you read about also says that if I take this figure like D and I take the point, as long as I move the point along a line that is parallel to the base, I'm going to have an area that is equivalent. So this triangle D here would be equivalent to this triangle that I'm trying to draw here, which would be equivalent to this triangle that I draw there. And so as long as the vertex point stays on a line parallel, then we are creating equivalent triangles. And so oftentimes the question is going to ask you to find areas in 2 different ways, and we might use either shearing or the additivity principle, additivity and moving principles, in order to be able to find these areas. In this case, you might think of this figure as having an area of 7 plus 5 as the base, or 12, times 5, which is the height, which is 60. So base times height would give us 60, divided by 2 would give us 30. We would then have to take that 30 and subtract out this area here, which is 7 times 5 divided by 2, and that would give us an answer. Or we could directly find this by thinking of this figure as having a base of 5 and a height of 5. 5 times 5 would give us 25, divided by 2 would give us 12.5 square units. Either way, we're going to get the same answer. Both ways are valid. In some cases, it may be more advantageous to think of it one way as opposed to another. So a quick review, we want to know about what the concept of area is. We want to know about using the additivity and moving principles to find area. We want to know about the area of triangles, the area of other polygons, and using the idea of shearing to find area. I will post a, the homework is right here. I will post this to our Sakai site, and like always, I'm available Thursday morning virtually, and in my other office hours. I'm also happy to meet at other times if you would like. Have a good week. Bye.